Okay, in this video I'm just going to do a couple more examples where we see mass going all the way over to becoming particles, or particles going all the way over to the mass. Remember that the mole is just a convenient unit to use when expressing the number of atoms or particles that make up a substance. Since the number of atoms is usually really large, we need a more useful unit to work with so that we don't have to write times 10 to the 23 or times 10 to the 24 every time we're doing something, so we convert to moles. But really, a mole is just a number of particles. So when we're dealing with chemical reactions or any other sort of chemistry which give us ratios between the number of particles, since moles are a representation of the number of particles, it's a really nice unit to work in. So in a typical problem for the whole rest of this course, we're going to take what we're given, we're going to convert it to mole, we're going to look at the interaction between the particles in the situation that we're dealing with. Often this will be a chemical reaction, to do a mole ratio if that's appropriate. And then once we get the number of moles of whatever it is that we are interested in the question, we'll convert that number of moles back out to whatever unit we wanted to use. So let's just see how that works for this question here. In a chemical reaction, 1.2 grams of hydrogen gas is used to make water. How many water molecules can be created? So we have 1.2 grams of hydrogen gas. So the mass of the hydrogen gas, 1.2 grams, and the molar mass of hydrogen gas, remember it's H2, is 2 times the 1 gram per mole molar mass of hydrogen itself. So 2 grams per mole. So, I don't know, equation. Mass over molar mass, or conversion, 1.2 grams. I want to get rid of grams and introduce moles. So every 1 mole we have 2 grams. Either way, I end up with 1.2 divided by 2, or 0.6 moles of hydrogen gas. Regardless of which way you want to look at that, remember these are the equations. This one was called the factor reduction method. Anyway, if that's the number of moles of hydrogen gas, H2, and we're forming H2O, there's some other stuff here, but you'll notice that H2 and H2 are in a 1-to-1 ratio. So if that's the number of moles of H2, that's the number of moles of H2O gas that we can create, or water molecules we can create. So if that's 0.6, then since however many of those I have the same number of those, this is going to be 0.6 moles. So it says how many water molecules can be created. So remember that moles is equal to the number of particles divided by Avogadro's number, or the number of molecules per, or the number of particles per mole. So 0.6 is equal to the number of particles. Avogadro's number was 6.02 times 10 to the 23. So that gets me a number of particles, which is 3.612 times 10 to the 23 particles. You could do that doing the factor reduction, of course, by saying 0.6 moles. I want to convert moles to particles. We know in 1 mole there's 6.02 times 10 to the 23rd particles, and so I multiply. Anyways, that's the number of water particles that we could create using this, or using 1.2 grams of hydrogen gas. One more time, the 3 steps. The 3 steps, convert it to moles, look at the interaction between moles or mole ratios, depending on what that looks like, and convert the resulting number of moles into whatever unit is required for the question. Okay. 1.5 times 10 to the 23 atmospheric nitrogen atoms were converted into nitrogen dioxide by lightning. What is the mass of nitrogen dioxide molecules produced? So, that's a number of particles that I have there of 1.5 times 10 to the 23. So I can convert that to my number of moles by doing my number of particles divided by Avogadro's number. So that works out to, hold on, I don't know what I did there, 1.5 divided by 6.2. So that works out to, that's not good. Try that one more time. 0.249 moles. Or 1.5 times 10 to the 23rd particles. I want to convert particles to moles. For every 1 mole, I have 6.02 times 10 to the 23 particles. Since it's on the bottom, I divide. Anyway, that's how I get my number of moles. Now here, I have nitrogen being converted into nitrogen dioxide. Again, here we have a 1-to-1 ratio. There's some other stuff here, it doesn't matter. But that's in a 1-to-1 ratio. So my number of moles of nitrogen, is equal to my moles of nitrogen dioxide. So I don't have to do anything with a ratio. Don't worry, in upcoming videos I will deal with a ratio here. But this is a 1-to-1 ratio, so there's nothing to convert here. So the moles of nitrogen dioxide are going to be 0.249 moles. Okay, with that in hand, I can figure out what my mass would be. I have to figure out my molar mass for nitrogen dioxide in the first place, though. So that means that I need 1 nitrogen molar mass plus 2 oxygens. 2 times 16 is 32, plus 14 is 46 grams per mole. And so, moles is equal to mass divided by molar mass. So 0.249 moles is equal to mass divided by 46 grams per mole. So I got 11.5 grams. So that's one way to figure it out. Or again, moles. I want to convert from moles to grams. For every 1 mole, I have 46 grams, and so I can convert. 11.5 grams again. So that'll be 11.5 grams again. So, again, looking at my basic steps here, take what's given, convert it to moles, figure out if there's any sort of mole ratio between the thing you have and the thing you want, and then convert the resulting number of moles into whatever you want for the question. So, here I had the number of particles, I converted it to a number of moles. It was a 1-to-1 ratio, so I had no need to change that, so that's the same number of particles or number of moles that would be produced of NO2 gas. I figured out how much each mole of NO2 gas weighed, and then used that, either by looking at it as a conversion or using the equation, to determine the mass of NO2 gas produced. So that's a couple more examples that show how, because moles represent the number of particles, we're constantly going to be converting into moles, dealing with the particle interaction, the chemical equation, or whatever it is that we have, and then converting back out of moles to determine the actual value that we're interested in.